All right, I have not got your test graded yet. Jared, I think, is going to take his tomorrow or Friday, so I will get them graded and have them back to you first of next week, if not by Friday. Today we're going to start on differential equations. Now, if you'll look on the board here on Moodle, here's a list of things that are due. All of that is due before missions week. So you need to do everything in your power to get all of that completed up. Because remember, when you get back from the mission trip, we only meet 3 days and the quarter ends. We've got a test on the third of those 3 days. So we're not going to have a lot due then either. We're going to be getting our heads wrapped back around differential equations so we can be ready for that test. So be sure that you're on track for this. You've got 3 FRQs due this Friday. You will not have any FRQs next week. That's all the assignments that you'll have between now and mission trips. So work on getting those done. So, some of you still have back work due. Try to go ahead and get that in. That's going much better in the last few days than it was a week or so ago. So I appreciate y'all's efforts to get caught up on that, okay? So if you haven't downloaded it yet, you need to download 35, which says Intro to Diffie-Qs. Whoops, that's not intro. That's the end of it. Well, why won't you go backwards? Okay. Differential equations. Now, differential equations are going to be very similar to what we've already been doing with integration. It's not exactly the same because they can get far more complex. But really, a differential equation is any equation that has the variables and their derivatives in it. A simple differential equation, you've already seen stuff like this because you've actually seen the words dx dy equals x. That's a differential equation. That's about as simple as it can get. But also, there's sometimes that the differential equations could get much more complicated, and we could have something like this to be a differential equation. Or we could have something like this where we've got the second derivative plus the first derivative plus x equals y. So we could get to all kinds of funny-looking and strange-looking differential equations. We're only going to touch the surface of these in this class. When you go off to college and study engineering or mathematics, you'll get an entire boring course on differential equations. You'll learn so little in it that you'll really enjoy it, okay? But that's what you have to look forward to right after the second course in calculus. But that's where you really delve into it. We're just going to kind of scratch the surface of them today, okay? So differential equations are functions that have variables and derivatives in them, and we're going to learn how to solve them over the next few days. First thing, sometimes they're so complicated that solving them is next to impossible. And we're going to learn ways that we can learn stuff about them in a scenario where they're just so complicated that we can't solve them. But first of all, let's look at some examples and let's see if we can determine some solutions. So this top thing here is a differential equation. Y double prime minus y equals 0 is a differential equation. The question is, are any of these things solutions to differential equation, to that specific differential equation? So, any suggestions on how we would attack that? Right. Find the second derivative, plug those two things in, and see if you get 0. If you do, then it's a solution. If you don't, then it's not a solution. So let's look at this first one. If y equals sine is my function, what's y prime? Cosine. And we need the second derivative, so what's y double prime? Negative sine x. Now, if we plug that into this equation, negative sine x minus sine x, what do we get? Negative 2 sine x. That's not always equal to 0, is it? because the other side of this equation says it should be equal to 0. Well, it's not always equal to 0, so what does that tell you? This is not a solution to it. If we had wound up with 0 equals 0, we would have. Now, something you can't do legally in these is you can't algebraically manipulate this initial equation. So you need to treat, do y'all remember doing trig identities? Where you had to work with the left side and work with the right side and make them equal? Think of it in those terms. I can manipulate the left side algebraically. I can manipulate the right side algebraically. And if I can get them to the same thing, poof, I'm good. But I can't just move something over. So now, we worked through the first one. Try this second one, y equals 4e to the negative x. See if you think it is a solution to that specific differential equation. Remember your chain rule when you're taking the derivatives, because the power of e is something other than just plain x. That's what I got for my first and second derivative, so be sure that you and I agree. I could be wrong, so if you think I am, let me know. So do you agree that that is a solution to the differential equation? Because when we simplify the left side down of y double prime minus y, we get to 0. We get to the point that we can say this equation, no matter what x is, this is going to be equal to 0, and 0 is equal to 0. So yes, it's a solution to the differential equation. All right, one more time, try the last one. C e to the x. What's that c mean? Constant. What's the derivative of c then? Zero. Very good. Y'all may have said it and I just didn't hear it, but it's 0. So be careful taking that derivative and see what you think that is. What's the significance of that being a C there? What does that tell you anything? That's right. As long as any number that we put there is going to be a solution to this differential equation. So e to the x, 2e to the x, 3e to the x, 4e to the x, pi e to the x, anything is going to be a solution to it, provided the number in front of e to the x is a constant number. So this is considered a generic solution. Okay? A generic solution. Sometimes you'll hear it called a family of solutions. Okay? So a generic solution or a family of solutions. And when you've got a generic solution or a family of solutions, you can graph that family like on this next slide. And when you graph that family of solutions, you should see a lot of similarities in the graphs. What you'll normally see, if you notice here, we got 4 different solutions to this specific differential equation right here. The DFQ is xy prime plus y equals 0. That's 4 different solutions to it. The dark black line is one solution. The lighter black line is a second solution right here. And the same thing, the dark blue line and the light blue line. 4 different solutions. And all solutions should follow that same pattern. So all of your graphs for potential solutions should look similar to this. If you'll think of it, do you remember when you were learning graphs and like you got x squared, and what does x squared plus 2 do to it? What does a plus 2 do to an x squared graph? Just moves it up 2. It's similar to that. The family of solutions should look like graphs that are just strictly moved around on the xy coordinate plane, up or down or left or right. So just realize that when you're graphing, or if you're asked to graph, sometimes you'll get a set of solutions that looks like that. Okay. Here's a differential equation. xy prime minus 3y equals 0. Verify that cx cubed is a solution. What does that mean? Verify that that's a solution. What does that mean? Exactly. Make sure. We're telling you that it is. It'd be the same as saying show that that's a solution. So go through the process to show that that is a solution to that particular equation. And then we'll worry about the second piece of it down here in a moment. Y equals cx cubed. So what do we need to do in order to show that it's a solution to this DFQ that we've got back here? Right, take the derivative and plug and chug. Take the derivative and plug and chug. So you should be able to do that. Very similar to what we were doing 2 slides ago. I have the utmost of confidence that you're capable of handling that. Now, some of you are very smart and you can look at that thing and maybe even close your eyes and see all in your head that it works. That's not good enough. I've got to see on paper that it works. So be sure that you show enough work to verify that that is a solution. Okay, that's the type work that I would do to verify that. Notice that I plugged the derivative in on this first line here. I took the derivative up here prior to it, then I just plugged it in here, leaving the rest of this DFQ just like it was. The next line I plugged in for y, and that's something that sometimes students say, I don't understand. Remember, we said y equals cx cubed. So algebraically, I can put that right there in place of the y. And then if you simplify each of those, they're identical, so they're going to be 0. Therefore, we verify that it's a solution. Yes, ma'am?
What about when you take the first derivative of y and doesn't have the plus c at the end?
You're thinking integration. Oh. If you integrate, it'd be a plus c, but since you're taking the derivative, no, it goes the other way. Yeah. See how confusing we're going to make this? You've got to go both ways at the same time. Okay. So we know that that's a solution. This is a generic solution right here. How do I know that's a generic solution? I've got a C in it. All right. Now it says find a particular solution determined by the initial condition y equals 2 when x equals -3. What do you think that's asking you to do? Plug in and solve for C. Okay. What are we going to plug into? Yeah, but which equation? I mean, we've got a DFQ, we've got y equals cx cubed, we've got y prime equals 3cx squared. The original function here, why do you think that, Mary? That's right. We've got y and we've got x in there, don't we? Why can't, Why is it more challenging to use the differential equation? We've got the derivative in it. So could we do that? Yes, we would just have to plug 2 in over here and get something for y prime. So if I were you, I would go back to this original equation, the solution, in fact, y equals cx cubed, plug the numbers in and figure out what c is. 2 equals c, 27. Now, c equals a number is not answering the question that's asked. The question says find the particular solution. So to find the particular solution, we're going to plug this number, negative 2/27, back into the original solution up here, and that is our particular solution. Y equals negative 2/27 x cubed. That's the particular solution for this specific situation that we've got here. Y equals 2x equals negative 3. If I give you a different scenario for y equals 2 and x equals negative 3, you'll have a different specific solution down there. But it should be of the form y equals cx cubed. Questions, comments, observations? Easy stuff here. Good. All right. Whoops, wrong button there. Slope fields. I cannot guarantee you anything about the AP exam in May. I can tell you out of the last 8 years that I've had students take an AP exam, every one of them have had to draw a slope field. That's all I can tell you for sure out of it. So eventually they're going to stop doing that. I don't know when. Considering that the scores are not extremely high on this particular problem usually, I would bet that they're going to continue putting it on there for right now. But what are slope fields, or why do we want slope fields? Slope fields are relatively new in mathematics. By that I mean probably only in the last 50 or 60 years have they been really useful to us because of computers now. Because as I said earlier, sometimes we can have a differential equation. It may look complex or it may not look complex. But it's simply something that is so difficult to solve that either we can't solve it or solving it would take so much time that we need to know information in a different way a little bit faster. Slope fields is a way to do that. And with a slope field, all we do is we take a differential equation and we graph it discretely at different points. So we'll take a differential equation and we will plot maybe 6, maybe 9, maybe 6,000 points, and suddenly we've got all these little bitty short lines of what the slope of the actual function looks like at that point. So just to give you an idea, what if you were to be looking at a slope field and you saw that the slopes at a bunch of points looked something like this? Do you have somewhat of an idea of what the curve probably looks like? If you were to guess, what would you think that probably is? Sine or cosine, something like that. Now, we don't know which one or anything, but then suddenly we've got some idea of what it looks like. Essentially, that's exactly what we're going to do. I'm going to give you a differential equation, and you're just going to estimate the slope at a lot of points and see if we can learn anything from it, okay? So the first task is learning how do we draw a slope field. So this says sketch a slope field for the diff EQ y prime equals x minus y for these particular points. Notice it's only giving us 3 points. We're just going to do this to be sure you've got some idea of what we're doing here. So again, this is not really an extremely challenging thing to do. You just need to figure out how you want to handle it every time. Negative 1, 1 is right here. 0, 1 is here. 1, 1 is here. Now, what I do, this is partially for me, but partially for the person that's grading my paper. I'm going to come over here and do a 3-column T-chart. Okay, when x is negative 1 and y is 1, I'm going to plug them in up here to figure out what y prime is. Y prime is negative 1 minus 1, so y prime is negative 2. The next point is 0, 1, so it's 0 minus 1, it's negative 1. The next point is 1, 1. 1 minus 1 is 0. So that tells me what the slopes are. Now I'm going to come over here and estimate those slopes. I'm going to start with the last one. 1, 1 says the slope is 0. What does a 0 slope look like? Horizontal line. So I'm going to draw just a short horizontal line right there at 1, 1, because that tells me what the slope is there. At 0, 0, the slope is negative 1. Now, you don't have to be exact on this, but you know that a slope of negative 1 should be falling, and it should be falling at about 45 degrees. So in my mind, I think, okay, this would be 1, 0, so I want it to kind of be pointing at that. That gives me a 45-degree fall to it. And the next one over, negative 1, 1 is negative 2. It needs to be steeper than that. I'm not going to get out, actually measure and be sure you're doing it exactly right. Just be sure that it's steeper than what this one was. Estimates is all we're looking for. And we could continue doing that for all the points. Why don't you go ahead and do it for negative 1, 0, 0, 0, and 1, 0. And see how those graphs... Hopefully you'll start getting some idea of what it looks like. So do the same thing for those particular points. And I'm going to be getting something else ready for you. Negative 1 minus 0 is negative 1. 0 minus 0 is 0. 1 minus 0 is 1. So over 1 up 0 has a positive slope. This has this. This has. Did you get something that kind of looks like that? Now, based on those three, you got any idea what the graph might look like? Probably you'd have to do a lot more in order to get, you probably have to do 30 or 40 at least to get a good idea of what the graph might look at. And that's one reason slope fields are much more useful today, because now you have tools such as this that can actually figure out what the slope fields look like much faster and much easier than we ever could. Notice this is our differential equation, x minus y right here, and that's what a slope field looks like from negative 10 to 10. So that's 1,000 points, this graph there. Now, how would you use something like that? Well, we need to kind of figure out, what do we think the graph might look like? That's very challenging to do, and you have to look at them for a while before you can see that. But when I look at this, I look at it as something that says it's very steep down here, and the graph would be doing something like this, because it looks like it's almost a line right through there. And then on the other side, it looks like it's very steep here, very steep, and then it's going to come down and get to be something like this here. Funny looking graph, isn't it? Now that may not be exactly what it looks like, and it's going to be moved around. I mean, it could be there, or it could be up here. It could be coming up this line right here and then doing that. We don't know exactly what, but it gives us some ideas that we could go in there and graph. Your calculator, I don't think it has the capability to natively, but there are programs that you can put on your calculator to draw the slope fields for different graphs as well. You'll never be asked to draw something this complicated. The most you'd be asked to draw is 6 or 9 points to just be able to plot them on there. Okay? But this is a neat little tool, and there's plenty of other tools out there that will let you do that. And you can imagine now, this is 1,000 points. Without the aid of a calculator or without the aid of a device like Desmos, how long would it take you to do that? Hours. Is it hard? No, it's just very tedious and very boring. So that's the reason slope fields are relatively new as far as mathematics goes, as far as being beneficial to us, okay? Here are 3 slope fields that we've got drawn. We need to match them to the equations that they have there. So take a moment, see if you can decide which one you think goes to each one and why. I'm much more interested in the why you think it than what you think. I'm very interested in how you're going to tackle this, to be very honest with you. Somebody give me some ideas of how they're going to tackle this. Plug-in points, okay? Which graph, which differential equations are you starting with? Okay, yep, just find some different points there. So, anybody think they know which of the differential equations goes with graph A? Okay, so let's see. If we find the slope at up here. Gotcha. Why did you choose that point? All right. Does everybody see what he's saying? If I look at -2, 2 on all 3 of these, they're all 3 different. So let's see what happens when I put -2, 2 in here. -2 plus 2 is 0. So that points me to this one right here. If I put -2 in here, which of those graphs, A or C, look like it's -2? A, boom. And then here, if I put 0 in here, 2 in there, I'm sorry, it'd be +2, so that looks like that. And you can check that at a few other points as well. I'd recommend that you check it at 2 or 3 points. Now, to really test, or to see what you can see, look at A, and what do you think the graph would kind of look like? It looks like a parabola. See, that one's a little bit easier to see. Now, it doesn't mean it's going to touch each of these lines, but if you go in here, you see that you could kind of sketch a parabola in here of some sort. And you know that if y prime is x, if you integrate that, you'd get x squared over 2, which is a parabola. So suddenly you're beginning to see how the 2 places connect a little bit there. Any questions about this? Okay, we've learned 2 things. We've learned you are able to show that something is a solution by simply taking the derivative, plugging it, and verifying that it works. Then we have shown you how to draw slope fields. So that's all we're going to do today. Tomorrow we will learn actually how to solve DiffEQ. So that's all I'm going to do. Y'all get started on some work of some sort.